4, and maybe all through IDE 5 as well. Okay, so today's topic is one that has a little bit of, it has more than a little bit, it has some significant conceptual overlap with 470. How many people in here are in CPD 470 as well? Okay, yeah. So, important fraction, but by no means a dominant fraction of the course. I'm going to try to impart some concrete particulars about what I'm going to be expecting from one of the requirements for this course, and that concerns the fact that I'm asking you for the modules of your program to record specifications or contracts that basically indicate what is expected of those modules, even if all the how is hidden, encapsulated. It's maintained instead within the methods themselves or within the classes. Specifications are going to describe what is expected, okay? And those in 470 will have heard large parts of this, but there'll be quite a bit of particulars that I'm going to be presenting here, which they won't have seen. This will have a possible revisit associated with it, depending how the architectures for your projects are shaping up. I might also do a follow-on lecture, not next time, but later in the semester, on what's called the Liskov substitution principle and safe subtyping, rules for creating subtype hierarchies of polymorphism that are safe, reliable, can be extended easily, etc. But today I'm going to be talking about some basic expectations for contracts and specification. And the way I motivated this in 470 was to talk about the fact that software is structurally and dynamically complex. It has lots of moving parts, lots of interconnections, lots of surprises, and complexity of software development is a big challenge for delivering value. And partly because of this, we break programs up into pieces. And we try to ensure what's called separation of concerns so that different aspects of the situation, say the GUI part, or say the database layer, or say the business logic, or say the client-side interface, or the layer associated with abstraction so you can work on both iPhones and Android phones, that's somewhat separated out. We talk about a separation of concerns here. Different types of concerns are handled in different areas of a program. Okay, and the idea here is that modularity is going to support a bunch of advantages. One of them will be we can divide the program up into pieces, with each of those pieces being created by a different person or different team of pair programmers or what have you. So we can have a sort of divide and conquer approach. But we can also, by virtue of separating them out, gain a number of other advantages, particularly those who are in 470. What other advantages do we get through securing modularity for a program by dividing things up into pieces? How does it help us? Besides the fact we can assign these pieces to be built by different people. Yeah.
Health and testing.
Good. So each of those pieces can be tested more readily because hopefully it has a well-defined function. Well-defined, it's not the right word for it. It's an ambiguous word. A well-defined job, a well-defined purpose. Good. How about another reason we might break it up besides testing? Testing is very important.
It gives us kind of flexibility, like one function doesn't depend on exactly how another function gets its results.
Good. So you've expressed, perhaps better than I can, some of the key messages of the this lecture, in fact. It's to allow for separation of evolution. It's not just we can get the person to create up front the different parts of the program. We can allow those pieces to evolve more or less independently, or almost independently, by virtue of the fact that they only depend on an interface to each other, a well-defined contract, where the details of how they're implemented, that's not something that I, as a user, should be counting on. So it gives a very clean separation between what I count on versus all the gory details of how it's implemented. That allows those gory details to evolve. As long as it retains the basic promises, the basic contract, then my code shouldn't be affected by your code's evolution. So this is huge. And that perhaps is the single biggest, most important message that motivates the use of these specifications, of these contracts. But what's another advantage? I'll remind you, those in 470, GCC minus O2 minus O3 Gprof.
Performance optimization?
Yeah, why is performance optimization aided by dividing it up into pieces?
So you can tell which module is slowing your program
Yeah,
down.
you can tell which modules slow it down. Rather than just saying, oh, the whole thing is slow, you can actually spot, oh, this function is taking 42% of the time right now. We can optimize that, okay? These are some of the important reasons motivating a modular description of a system, modular characterization. Okay, now the key to modularity, or a central key, is abstraction, handling many particular cases in one place. And we talk about this as occurring through two major mechanisms, although in 470 I'm introducing some additional ones over time. And the one we're most familiar with is abstraction by parameterization. From 115 onwards, you've been creating functions or methods that take in parameters, and depending on the value of the parameters, the details of exactly what they do differ. Maybe the parameter is a particular array to operate on, or maybe it's the number of elements that you want to search, or what have you. And you can reuse this function at many places because it takes parameters. You can reuse it in the same code base or different code bases because it has generality by virtue of those parameters. But the thing we're going to talk about today is abstraction by specification. And here, we're creating something that's more general by ignoring implementation details. Instead, we basically say, look, anything that adheres to a specification, anything that adheres to a certain contract is okay. So we will support many particular implementations of this thing as long as they adhere to the same specification. And this is going to give great flexibility to the designers. Okay, I'm not sure why the spacing of this got screwed up. But the major, so I'm going to go on to specification because our time is limited. So basically the key to abstraction by specification is we separate the interface of a method from the implementation of that method. When I say separate, what I mean is we specify in different places and we give information about them out with different levels of readiness. So the idea is that other people besides the developer of this particular code should be operating just off the interface, this contract, what this code promises to do. The implementation details are purely the province of the people who are creating it. Someone else might have access to the code, someone who's going to use it, but they shouldn't be counting on that code. They should count only on the interface. And they shouldn't have to know about this code to know what this code does, what it does. The how, that's up to the person who implements it, okay? So the details being hidden, when we talk about abstraction, handling things in a general way, we're talking about hiding details, abstracting over details, not being caught up in the details of the situation. The details being hidden here are differences between implementations. two implementations can be different, but they make use of the same interface, and that's the key thing. Okay, we're going to spend a lot of time this lecture seeing these interfaces. What benefits do they offer? Well, locality. We can build one piece without knowing about the details of how another will be implemented. If A calls off to B, so here we have A, and here we have B, and if A is calling B, maybe these are methods, maybe these are classes, but A doesn't need to know all the details about B. All it needs to know is the interface, okay? It needs to know what it accomplishes, but call this method. What does it need for parameters? What are the legal values for those parameters, the legal ranges? What does it return? Are there any other changes made, etc.? So that's one benefit, locality. Modifiability is another one. We can change B without A being broken if we just change the implementation details. As long as we guarantee the same interface, A should be unaffected, because it shouldn't be counting on the implementation detail. It should be counting on what this accomplishes, not how. And what it accomplishes is as promised in a contract. And I won't go in, but there's some additional reuse benefits that can be considered as well. And the goal here is to buffer ourselves against change. If something changes, maybe the underlying technology, maybe it's client needs, maybe it's performance concerns. We can change B without having it ripple through, and we change B, it breaks everything else. That way lies madness. We want to be able to change things in isolation without breaking the rest of our program. People talk about the interconnected world of the internet and how that interconnected world is allowing us to achieve amazing things. And it's true. But as Dave Gifford said 25 years ago, we don't want a world that's we want a world that's interconnected in a robust way. We don't want it to mean that the wireless network going down over here in Thorvaldsen crashes computers over in agriculture. Crashes computers over in Europe. We want it to be robust. We want to, when there's a change in one place, we want it to ripple through to changes in a very small number of other things, if at all. We want to have very localized changes. Okay. So a lot of the art here is hiding details of things we anticipate changing frequently. We build abstractions that let us just slot in a new change that's anticipated, new type of change, and the rest of the code stays unmodified. So we might put in a function that returns the values to be used in a menu rather than hard coding. So when those things change, we just update that function. We're off to the races. Or better yet, maybe we put in a config file, or we have it loaded from a database, and we don't even have to recompile. We just update the config file, or we update the database. We're off to the races. The menu changes accordingly. We basically prevent ourselves from being broadsided by change by putting in place abstractions that are appropriately general. And one of the key ones is putting in place these abstractions. Okay, so imagine sort of the anti-pattern here. We have code that uses a first cut algorithm, which happens to be bubble sort in the strawman. So here's some code named foo and bar, and in both cases there's bubble sorts within the code. There's a bubble sort placed directly within the code in two of these places. And there's an issue here, because if we go and we want to update this code, to do more efficient sorting, we will go maybe modify it someplace, but we might forget that there's other places in the program where we need to modify it as well. This is like a best case. We just need to go find all the cases where this is used. But there might be other places where it is used in less obvious ways, maybe through reflection or other things, and we might not remember to update it properly. So, here, through abstraction by parameterization, we might hive off a method. And basically, instead of hard coding a bubble sort for price in one place and hard coding it for ages in another, we have a method which takes in different parameters. This is actually a array of doubles called values, and we can pass it, ages here and price here when it's in one place, and it does the jobs for both of these. Because it's in one place, it can be updated if we want to do so to a quick sort, for example. Okay, so we can update sort to use a quick sort. And that's all nice. That's abstraction by parameterization. And it's familiar, right? You've been doing this since 115. Instead of hard coding things there, you create a nice function which does it in general, and you call up to it from multiple places. And that's great. But for our needs today, that isn't enough, because there may be dependencies in this code as to the nature of what this sorting does. Maybe this code is counting on ties being in the same order. So if we have price, some initial indices, and two of them have the same, in fact, price, maybe we're counting on the indices associated with them being retained in the same order, not being switched in terms of order. So if A before, if index A is before index B, they both are associated with the same price here, then we're going to be retaining them in the same order within the sorted code. So the question here is, how do we update sort for abstraction by specification? How do we update this without breaking these two places in the code? How do we update a sort routine to a faster sort without having some fear that it's going to break things in lots of places? That's the question. Abstraction by parameterization got us this far. That's great. It's a big step. We have a separate function, and someone else can develop it, and we only have to change it in one place. All that's good. But abstraction by specification is asking, how do we prevent this change in red from breaking these two things over here, all these uses of it? And it's a non-trivial issue. And so, here, someone might go and try to look at the sort code to make sure the assumption is met. But the problem with looking at the sort code is what? Why is that not enough? Why is it not enough to say, well, I have access to that code base. I can go look at the code and see if my assumption holds. Why is that not enough?
It might not hold in the future.
It might not hold in the future. That sort might evolve further. Maybe they end up implementing a radix sort later or whatever. They change how sort is implemented to be a different sort. And the real question is, am I counting on something which I shouldn't be counting on over here? Am I counting on something that's not guaranteed? The question is, what is sort guaranteed? What things are they going to change and what are they not going to change? After all, they hopefully will not change sort to sort from least to most and change it after that from most to least. I want to know what can I count on about sort? What types of functionality are guaranteed with it so that I can use it appropriately or decide not to use it, right? So the key question is, how do we define this interface? And just knowing that some things has this certain signature, like it's okay. This is here. I'll move this over here. There we go. There we go. Just knowing that this is of this signature in star sort double values. Just knowing that that's the signature is not going to be very helpful to knowing what is guaranteed. Does it preserve the ordering associated with different indices? Does it sort from least to most or most to least? Ascending order, descending, in other words. How does it handle if this is zero length? How does it handle a null passed in? These are things I want to know. Does it allow that, right? Okay, so the question is, how do we define it so that that's clear? It's not sufficient to just give the signature. It says it takes an array of doubles. and returns and int stars. Sorry, that's not enough. I mean, that's grossly insufficient, right? We want some way of knowing what it does without having to look at the code. Why not look at the code? Because the code might change. The code might not be available, right? Often we're using jar files, we don't have access to the code. And thirdly, we don't want to have to go look at the code because it's just more overhead. We have enough to worry about in our neck of the woods. Why do we have to go puzzle out how someone implemented it? That obviates or sort of undercuts this idea of separation of concerns and separation of work, of divide and conquer. So here we're seeking a form of contract. What can I count on sort to do? What can I not count on it to do? What does it need from me to do its job? And so we achieve that through specifications, and preferably designed by contract. So the idea here is that we have foo and bar, and they're going to call off to something that's better named as sorted indices. That's what its name should have been. And sorted indices is going to have a specification associated with it. And it's going to state preconditions, postconditions, and generally what is to be expected, right? So here it says, given a double array of values, returns an array consisting of permuted indices of the elements of the original array, with the ordering of these indices being such that the elements at those indices are arranged in ascending order, smallest to largest. So the precondition is that values cannot be null. You can't pass it a null value and expect it to do its job. And the postcondition is the return value specifies for each sorted element the index where those elements originated. Ties, values with equal value, retain their original order. That's what I can count on, okay? As for the details, that's for the people who are going to implement it. I don't have to worry as long as that contract is met. So this is a contract of sorts. And you could say, well, it's still imprecise, and I'll grant you that. But it leaves a lot less chance of mistakenly assuming something or of rushing to some assumption than having no contract at all. It's a lot better. Okay, it's a big step forward. It will rule out whole classes of misunderstandings or errors. It will rule out counting on things that may change. It may rule out not knowing if you can count on things and just guessing in a hazardous way. Okay, so here, for the users of sort, the people who use sort, foo and bar in this case, there's specific guarantees on what they can count. And delineates assumptions on which you can't count. You can't count on this. If it doesn't mention it, you can't count on it. Unless you can logically deduce it from what is said. And it eliminates the need for guesswork, access to the code base, reading the code, and fear that the code may change, the code that's being used, the sorted code. For the creators of the abstraction, it's a big win. Why does it help the creators of the abstraction? Why does it help the folks who created sort? You can almost read it. Why does it help the folks who created sort? Sorted indices. Why does it help them?
Because they know even in the future how it's supposed to behave. Like maybe the person who created it leaves or gets sick or something.
Good.
They can.
That's good. Yeah. It helps them test the code. It helps them know what the code does for spreading knowledge around. It also helps them know how they can change it very readily without worry it's going to break things, right? Break the clients of the code. I mean, people who use code don't like to be told, oh, a new version of this library came out, now your code doesn't work anymore. Go change it. That's not a favorable thing for any of us as developers. So when we go and we modify our code, we'd like to be able to hope, with good reason, that the code that uses our code won't break. Otherwise, we've delivered, we've actually hurt others in our updates. So here, the creators of abstraction can actually evolve that interface, right? Clear understanding of what can be freely modified, and knowledge of what features users can count on, right? So another thing is they can write test code against this contractor interface before it's even implemented. Okay, some indirect benefits. So you get conceptual clarity on what's going on, easier integration of different components, easier understanding of the code, clear documentation of derived requirements, and in some cases more aggressive optimization because you know what can be readily changed, and easier quality assurance. Okay, this takes time. This is not free, but it saves a lot of time, and I would argue the time that it saves in terms of more efficient testing, in terms of effective peer review, in terms of fewer bugs that have to be debugged, and that in terms of extra iterations of testing after those bugs are fixed. Often there's very big time savings, okay, for rolling out these specifications. You can have early opportunities for review of detailed design because you know what this code is supposed to do. You can directly derive many assertion checks. Remember we talked about assertions last week? Assertions, exceptions, errors. You can directly derive many assertion checks from preconditions, postconditions. It's a gimme. In some languages like Scala, you can there's beautiful constructs just for checking the postconditions after the code returns. There's a special way you can say ensures this, or it can actually check it directly. For mocking, you have derivations of conditions to check in mocking. So you're creating a mock for B. Now you know things that it can check. For example, that all calls to it pass it a non-null value for values. It's being passed no cases where what's being asked to sort is based on a null reference, right? So we can know some things we could check in a mock, right? And what things to ensure in the return values from B. An easier test case condition, and as we'll see, less risk of violation of Liskov substitution principle. We'll see if we can feature that in this course. Certainly, that's going to be a notable part of 370. Oh, sorry, 470. Okay, so basically we can reduce risk of error, enhance speed of development. We can enhance performance because we're clear what we can evolve, what we can change without breaking things. Our code isn't ossified into sort of a low performance state. Okay, so contracts. This is all going to be about contracts. Contract is going to define an agreement between the implementer and the clients, the people who use this implementation. The things that call this sorted indices on the one hand, people who use it, and then the folks who implement it, the implementers, okay? And the contracts are going to be described by specifications, and these specifications change. Over the years, they've gotten a bit more formal, a bit more standardized, and there are systems where they are getting very formalized to the point you can automatically prove correctness. Those of you in 340 this term might be interested to know in some past versions of 340, there's been a language taught that does automatic proofs of correctness of programs, and that's been used to prove correctness of parts of the Linux kernel and the whole of the GNU compiler, for example. Prove that it is correct in terms of its treatment, in terms of that the implementation achieves what is promised. Okay. So there's going to be several levels of contracts that can be provided. We're going to look at preconditions, postconditions, invariants, and history properties in this broader class, at least the first two today. Okay. So with the specification, we will need to balance not providing too many guarantees, but providing enough that it's useful. So what's the problem on providing too many guarantees? So suppose you're the creator of sorted indices or another piece of code. What's the problem with providing too many guarantees?
Limits evolvability.
Yeah, it limits the evolvability of that code. Now I can't easily change things because I promised too much. I've tied my hands. Okay, how about giving too few promises?
They might as well know the implementation.
Yeah, people might say, well, wait a minute, I don't have enough here to count on. Either I'll use a competing library or, a different library, or I'll wing it. Sometimes people wing it. Sometimes people, capital P, wing it. So, I mean, we've all been in that situation, right? I think let's test it out. Yeah, it seems to kind of work. Okay, let's go for it. Or they may check out the code and say, okay, does this code match it? Very hazardous because that code might change, right? Check out the code now, it's fine. Next version of the API, broken, boom. Shouldn't be counting on that. So, you want it to be detailed enough that users can count on certain key functionality, rules out implementations that don't meet certain needs for them, and general enough that the people who created it can change the implementation, clear enough to understand, right? You don't want to unnecessarily tie your hands as far as evolving it, but you want to provide enough information to let the people who use it get the job done. So this is what I want to see in your contracts. This is what I want to see in your code base. As the code plans come into place, even before some code is written, these are the things I want to see. For methods, preconditions, and postconditions. Okay? Preconditions are the requirements for it to do its job. It needs certain things to be true. This needs to be non-null. Now, what does that mean? On whom is the onus put? On whom is the burden put? If we say, you can't call me with a null value of values, who's responsible for guaranteeing that then?
The person who's using.
The person who's using it, right. So the user, the client of this method, when they're going to call it, they're going to have to be sure, okay, that's non-null. If they have a null one, and they'd like to call this, well, there's no guarantee it will do something meaningful. It might throw an error message, it might throw an assertion during testing, so they've got to handle that case themselves. They can't count on this to handle that case, okay? Preconditions are things that the caller has to guarantee are the case. Now, it's still a good thing to assert that these things are the case, because after all, someone has messed up if that precondition is not met at runtime. If you do an assertion on these and that's not the case, some developer has screwed up. May not be the developer of this code base, although it could be if it's recursive or it's based on a previous call or what have you, but someone has called that without being careful what the preconditions are. Okay? Postconditions. These include return conditions and any side effects, any modifications of program state. These only are guaranteed to apply if the preconditions are met. If the preconditions aren't met, the user who calls this shouldn't be counting on any behavior. Basically, this is the information it needs to do its job. If it doesn't have the preconditions guaranteed, if the preconditions are not met, all bets are off about the postconditions. The postconditions are conditional, are contingent upon the preconditions. So you don't have to worry with postconditions that you have to deal with a failure of the preconditions. You can simply assert the preconditions. I'm assuming these are true, and then adhere to the postconditions. But you do want to say something about the return conditions and side effect modifications. Now, don't get caught up, please. Don't get caught up in the idea that all preconditions and postconditions have to do with things like this is non-null, or this is greater than 0. The return value is greater than 0. A key part of postconditions has to do with what job is being accomplished? So when we go back to this, you notice a lot of what's promised here, both up here, sort of post conditions are applied, the description of what this does, and in the post conditions, is something about what's happened. You know, it says, for example, values with equivalue retain their original order. Here we've indicated that it returns an array consisting of the permuted indices of the elements of the original array, with the ordering being such and such. So these are the things that people are counting on. What's formally in here in the post conditions and up here. Those collectively are part of kind of the post condition contracts. That's what it's supposed to do. And often it's quite detailed. It's not merely about, is it non-null, is it greater than 0, or what have you. It's about what it accomplishes. Okay? So that's post conditions. And I'll be looking for that in your code. Now, beyond that, I'm looking for 2 additional things. And those in 470 will be seeing these explored in considerable depth when it comes to what's called the Liskov substitution principle. And these apply to classes, apply to object-oriented context. And they consist of something called invariants and something called history properties. So I'd like to see, for classes, a statement about what the invariants and history properties are for this class. Okay? So invariants are things that are true at any time. At any given point, these things are true. For example, this data structure might be non-empty. It might have no duplicate keys. It may have, no values in it for any keys which are duplicates of each other. The quantities of the values stored in this data structure may all be non-negative. We may have, or the current value stored within this data structure may always have length greater than 0. So at any given time, these invariants should be true of an instance of that class. Any one time we could check that. Ladies and gentlemen, these invariants, these are not about particular methods. These are not things that are specific to one method, one function. These are things that are guaranteed collectively by the set of methods supported by the class. The implementations of those methods guarantee these things. That they will never conspire with each other to lead to a case where the length of the item stored in the dictionary has a length of 0, for example, or where there's a duplicate. These are things that are resulting from the emergent behavior of a set of different methods. So these are not reducible to methods. They are invariants that are guaranteed by their interaction. Okay. Now, certainly no post condition should violate this, but this is something we could check at any time, regardless of whether invoking a method. We could check at any time for an instance of the class that this is true. The next thing is history properties. And here, we are, so with invariants, we're considering at any one time what things are true, what things are guaranteed to be true, must be true. The representational invariants, as defined in one of the books I recommended for the class, Program Development in Java by Barbara Liskov and John Gutek. It has a good discussion of representational invariants. History properties are different. History properties consider 2 points in time, A and B. One is later than the other. And these are properties that hold between those 2 points in time. So maybe, for example, the value of a counter never declines. It never goes down. So if we have this point in time and a later point in time, it cannot be less at the later point in time than its value at the first point. That's an example of a history property. Another example of a history property, ladies and gentlemen, would be the fact that this class is immutable. What do I mean by immutable?
Once it's created, it can't be modified.
Yeah, once it's created, it can't be modified. It is a value class. It cannot be changed. And probably in this class, and certainly in 470, we're going to be talking about why value classes are so valuable, why they're so useful, why they simplify our job as programmers, and why they actually support stronger performance by allowing us to optimize code, allowing us to parallelize code, and support building of data structures out of them, using them as pieces that are considerably easier to put together than with mutable constructs. The point is, immutability, invariance to change. The fact that it does not change, it is read-only. You can use different names for it. That is a history property. Between points A and B, it always retains the same value. That's a history property, and that might be true of a given object of that class. And again, it's something that is guaranteed collectively by all the different methods. And what this is saying is there is no method that changes this. If you have an instances object and you ask it for some property, that property is guaranteed to have the same value at a future point in time. Okay? So that's an example of a history property. Are people comfortable with that idea? So there's, for methods, for each method, preconditions, postconditions. I'm expecting to see that at a very basic level. And then for classes or objects, there can be invariants and history properties. These are things that are true for that method as a whole. Yeah.
So for an immutable object, like what would be the starting point for the history property? I'm just wondering like why it wouldn't be an invariant that holds for the whole lifetime of that instance.
The deal is that, so good question. Invariants are things that you can check at any one time, okay? And it's hard to say, well, you can check that it's invariant, that it hasn't changed at any one time, because you're only seeing it at that point in time. One way you could phrase it as an invariant, and I'm not opposed to this, I mean, I'm being strictly pragmatic about it. You could say the invariant is, the properties at any one time are the same as the properties by which it was created, for example. But there you're implicitly referring to the time it was created and now. You see what I'm saying? So I think it's easier to think of it as a history property. To really verify it, or to verify that it's being violated, you need to consider 2 points in time. It's hard to check whether or not it's violated at just one point because you don't know what the values were earlier. I don't know if that helps. Other questions about this? So be looking to see these included. Now, these invariants and history properties are other things you can check. So for example, in methods, when you have assertions, you might be checking the invariants. Check to make sure that they are true. You might have tests that confirm the history properties externally. These are things that we put into place, not for documentation's sake. We put into place because people may be counting on them. Look, when you have a library and people use your library, those people want to know what your code does and what they can count on. And if they're serious users of your code, they may really study the documentation for what can I count on here. And giving a statement of invariance, what things are guaranteed to be true at any time, and history properties will not only help the testers in your team, it will also help those who use this code, maybe elsewhere in your team or beyond, to know, to make sure they understand it. Make sure they understand this code. Okay, so here's some examples. Promise some examples. when we talk about the list scope substitution principle in 470, we're going to be going through a lot of examples like this. Here's a class. Read only int set. Okay. Here's a constructor for it, and here are two methods for it. You notice that for each of them, there's some post conditions specified. For example, for has, it says returns true if and only if element, that's the argument here, it's the parameter, is an element of the set represented by the method in which this is imposed. So you have a method of type read-only inset. It's a reference to a read-only inset. Call it R, and we call r.has 2, and it tells us whether or not 2 is an element of the set. Right? Precondition null here, or none. There's no precondition. Int by implication can be any value. It can be -1. Could be max int, what have you. Any value is a candidate. It's an iterator for the elements. It iterates over the elements. The set will yield each element of the set exactly once in an arbitrary order. I don't give an order that it's rising. And here's the specification for the constructor. You notice I do document the constructor. Initializes this to represent a set conditioning. Represent a set consisting of the set of integers contained in elements. Set consisting of the. Okay, here's an integer set with preconditions. It has, remove, subset, etc. What's an invariant, or tell me a history property for this one. What would be a history property example that holds for this guy? Should really actually state this explicitly, because you can imagine a case of funny business given that this is Java. What history property might someone want to infer from this? It'd actually be a little bit uncertain.
It always has the same elements it was created with?
Yeah. Why might they be uncertain about that? Well, why might they have some confidence that might be a reasonable assumption?
Because it's called read-only inset.
Okay, it's a good start. Yeah, yeah. So that's a good start. What else?
There are no methods to mutate it?
There's no methods to mutate it. Why might they be uncertain? Reasonably so. If it doesn't say explicitly this is immutable, why might they be uncertain about whether it is mutable?
Where it's explicitly stated?
It doesn't explicitly state it. And what could happen?
Some of these methods could have side effects, like maybe if you're getting an element, a user might expect it to be removed if it's not explicitly stated.
Okay, that could be, but there's actually something more nefarious that could go on.
Elements can be modified outside?
Yeah, exactly. Okay, so I pass in elements to the constructor. Maybe it just goes and uses that internally to point to the elements for itself. And then I modify it subsequent to that. Subsequent to that, I change what's in elements. After all, I just give it a reference to some array, and it says, oh, well, I'll use that array for my elements. And then after I give it to that, I go and I overwrite that array with all sorts of random integers. And suddenly I've modified the internals of this class. So if that's something I should count on, if I should be able to count on that as a history property, that this is a variant, it really should say that, because otherwise someone might not know, can they count on that? And they therefore might say, oh, well, maybe I better not change these values. They might not even notice it and overwrite it and still be counting on it implicitly because of the name. So this is a case where it really would benefit by providing some guarantee about that. Incidentally, that's one of the reasons why if we have read-only data structures if we have data structures that are immutable, that cannot be modified, it's a lot easier to build things out of them. We don't have to go copy this, because the way to deal with this is what? Make a copy. Say, oh, I'll copy that array and store it internally. I'll store a copy. I won't store actual reference to this guy, I'll store a copy. So mutability, ladies and gentlemen. You might think immutable things are really inefficient, because if you add something to it, it makes a whole new thing, but they allow huge amounts of sharing. And they allow for easy parallelizability, other benefits. But one of the big benefits is they allow sharing for many particular things of underlying data structures. Whereas mutable things like this elements, to build things out of them, you actually do a lot of defensive copying. You copy things just in case, so it can't be modified. Okay? Anyway, this is something where we could have had a invariant, or we could have had a history property set. Here's an integer set. This is not a read-only integer set. This is a mutable integer set. And you'll notice, I want to emphasize how some of these things are defined. You might find this a useful pattern for your code. For example, the insert function here. It actually refers to, as a precondition, something that says has of x. Where is has of x defined? Indeed. Right up there. So one common pattern you'll see with preconditions, postconditions, is that the preconditions and postconditions could refer to the values of other methods as called on this. So what this is saying is, you can call insert of x on an instance of integer set only if calling has on that element returns false. And that boils down to saying, okay, it's not in there, it's not present in the set, but it makes it more specific, it makes it sharper. It also provides hints to testers for how to test this, because now they can test, okay, is this precondition met? If so, call this appropriately. And you notice the postcondition here also refers to has. So the precondition is it does not have it. Postcondition it does have it. And there's an initial comment there. Okay? So postconditions and preconditions for different methods might refer to each other because they have to work together. They have to work consistently, right? Similarly, remove, right? Precondition is none. They might be surprised at that. What is that telling us? What case might we be if we didn't have this precondition? What thing, as users of this class, what thing might we be worried about? About what thing might we be worried?
If something exists,
Yeah.
or
So
doesn't exist.
yeah. So if we call remove on something that isn't present, is it going to blow up, right? And the answer here is no. We can call remove on something that's not in there. That's fine. The postcondition in any case is that after calling this, it's not going to be in there. So if we call it as something that's already not in there, that's fine, is what this is saying. So it helps relieve a developer's worry, oh, I got to check, is it in there? No, you just call it, and if it's not in there, whether it's in there or not, it won't be after I call it, right? Is subset. Okay, I would argue this is actually a poor postcondition. It needs to be sharpened. I would argue that there's something flawed with it. What's flawed with this? Okay, so is subset. So here we have an integer set and we ask, is this other integer set a subset of the one on which I'm calling this? So I have a set A, and I call A dot is subset capital S. Capital A dot is subset capital S. Why is this somewhat ambiguous here? Returns true if this is a subset of S. This, in this case, A. Because A, I call A dot is subset. Why is that ambiguous?
You don't know which one is a subset of which.
Well, it says if this, so that's the one on which it's invoked, say the current object, is a subset. So B is A, a subset of S. But there's a different ambiguity. Good guess, but there's a different ambiguity here.
Whether or not it's a proper subset.
It's, yeah, is it, when we talk about subset, do we mean proper subset or subset? What would be a case where it might be considered loosely a subset, but it's not a proper subset? If they're the same, right? So probably it would be good to have a further explanation in here, or to, say proper if that's what's stipulated, or to say, if the two sets are equal, it will return. It will return true. Just to have a further clarification here. Union returns a set consisting of the elements of the current set and of set B. Notice I said current set here. I could have said this, and of set B. So here we've unioned. We've taken the union of them. Okay, so some important patterns and critiques here in terms of ambiguity. So, well-documented code can eliminate worries in the parts. These are from the Liskov and Gutag book. So here, ladies and gentlemen, we have a counter object, and initializing it, calling the constructor, makes it contain 0. Get gets the current value, increment increments the value. That's what we have to go by. What might we deduce from that? What history property might hold?
It's always greater than 0.
Okay, that I would argue is an
Oh, yeah.
invariant.
Then it only goes up.
It's always 0 or higher is the invariant, right? At any one time, we could stop at, how could it be less than 0, right? I mean, it starts at 0, it can only stay the same or go up. So it's got to be 0 or more. So that's a good invariant history property. Yeah.
It can only be greater than or equal to itself at any point in time.
Okay, so let me rephrase that if I could. It never declines. It never, it always either rises or stays the same value over time. So that's something we might deduce through this. Now, as those in 470 will learn, and maybe in this class we'll talk about it a bit, this imposes, if we're counting on this, look at this interface, this imposes real strict constraints on any subtype of this. We can't create a subtype that is a nice nifty method set that sets it to an arbitrary value. Because all we know is that it's a counter. Secretly, it's a fancy counter, but that breaks the assumptions that we reasonably came up with from this interface. So that will have to do with safe subtyping. Okay, my read-only dictionary here. Abstraction represents a map from keys to elements. M is a set of relations. So here's several methods. Here's a my read-only dictionary, keys and elements. The precondition is the keys have there's the same number of elements, and the keys that it passes the elements itself. Okay, and two keys are equal. Basically, there's no duplicated keys. In other words, if key sub I equals key sub j, it's got to be that I is the same as j. There's no cases where we have duplicated keys. Okay, and that holds for all elements here. So the post condition, this is set to represent a map from keys to elements. So that's the post condition of the constructor. Here we have get element. It takes in a key. The precondition is the key has to be non-null here. Okay, the keys are strings. key has to be non-null, and the key length has to be greater than 0. And M contains mapping from that key to some D. So this is saying this got to be, if we're saying get element, there's got to be this key already in this data structure. M contains a mapping from that key to some D. And the post condition returns the V such that key, the key is associated with that V in M here. So this specifies get element. And an important consideration is, if we say get element on a string that is not present in this, we're violating the precondition. It's counting on us only asking for things which are in there. Here is occupied, it returns a Boolean, and here the string has to have certain rules associated with it. It returns true only if there's a mapping to that, and otherwise false. So these are examples of preconditions, postconditions associated with this abstraction. I think you get some of the ideas here. We try to specify rules here. Now, you may again say, wow, this is going to take some time. It does take some time, but it makes it super easy to write assertions after that. Makes it quite easy to test it. Makes it quite easy for someone else to understand it. So yes, it takes time, but yes, it takes away time from other tasks, which you've got to attend to anyway. Answering questions from someone. How does your code work? What is it counting on? Can I pass it a null value? Can I give it, why is it throwing an error for an empty string, etc. Okay? So these things will take time. I give a bunch of examples here. These are actually from Effective Java, or from, and I should make sure the citations are in here. But what we're looking for in the class is this declarative specification. This specifies what is guaranteed, abstracts away from how. Not very detailed specification of exactly how it works. So we're looking for this type, the what, okay? And for those who are interested, I do include in here some stuff on formal specification languages, which can be checked by a compiler and used to actually prove things, okay? Very good. So that's all we have time for today. Thank you very much. That's all we have time for this session. We have time, most certainly, for your presentations later this afternoon, okay? So I'll look forward to that. Thank you very much.